Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to learn how to jointly simulate multiple random variables within the same probabilistic model. This is a very important topic in practice because, as we discussed when we introduced the Monte Carlo method, it is often the case that you cannot compute probabilities within your probabilistic models explicitly. You have to perform simulations in order to approximate probabilities of interest. Therefore, it's absolutely critical that you're able to jointly simulate random variables within the same probabilistic model in a correct way. Let's take a look. We're going to learn how to exactly do that, jointly simulate multiple random variables. And again, the goal is to get the joint distribution right. We will see what I mean by that in a moment. We're going to focus on a very simple example where we have this triangle lake where, if you remember, we're modeling the position of an aquatic creature, an otter, that is living in this lake, and we assume that the density of probability for the location of the otter is constant. What does that mean? It means that the density in here is non-zero and is constant, out of the lake is 0. So what is that constant equal to? It has to be equal to 2 because the area of this triangle is equal to 1/2, and the joint density must integrate to 1. This is the joint density of the vertical coordinate and the horizontal coordinate. Our goal is to simulate samples of the vertical and horizontal coordinates that have the right distribution, that have a distribution such that the joint corresponds to this joint PDF that is triangular. So we already know how to simulate a single random variable. If you don't remember, go check out the video on the mystery function on inverse transform sampling. But the idea is relatively simple once you understand what is going on. So in order to generate samples from a certain random variable A, we need to know its CDF, f of A. And then what we do is we generate samples from a uniform random variable in the unit interval, and we feed those samples through the inverse CDF of A. Again, if you don't remember why this enables you to simulate the distribution of A, check out the video on inverse transform sampling. But here we're going to assume that this works out. All right, so now we can say, okay, we know how to generate random variables. How about we just generate the vertical coordinate and the horizontal coordinate and see what happens? In order to do that, we have to derive the marginal PDF of A and of B. We already did this in the video of marginal distributions, but let's just use this as a very quick review. We want the marginal PDF with respect to A. What do? We integrate over B. So just to be clear, what are we doing? We're integrating over B at different points to obtain the marginal of A at those points. So we integrate 2 from 0 to this line. What is this line? This line is A plus B equals to 1. So at that point, B is equal to 1 minus A. So we integrate 2 from 0 to 1 minus A. We obtain 2 times 1 minus A. That's the marginal PDF of A. By the same argument, because there's a symmetry here, if we start doing it with B, we're going to get that the marginal PDF of B is 2 times 1 minus B. But in order to apply inverse transform sampling, what we need is the CDF. How do you obtain the CDF from the PDF? Integrate. In this case, we integrate from 0 to A, right? Because realize that the marginal here of A is not 0, only between 0 and 1. In order to obtain the CDF, that's the integral from 0 to A. It's the probability that this random variable is more or equal to a certain constant A. So basically, we just need to integrate this guy. Again, from 0 to A, the integral is very easy. It's 2A minus 2A squared. Now, inverting this is not that easy. Basically, what you need to do is set this equal to U and find the A that gives you a certain U. I used to do this very well in high school. Now, by hand, I'm not so sure I will be able to do it. I guess I would just look up the formula. Anyways, you can check that this value is actually correct. I mean, I am able to do it because I did it originally to create these slides, right? So yeah, you can check that if you plug that in, that's the inverse of the CDF. So if you feed in uniform samples through this formula, you're going to get samples from the marginal PDF of A. Awesome. By the same argument, by the way, as I said, the marginal of B is 2 times 1 minus B. So the CDF of B is 2B minus 2B squared. So we can use exactly the same formula, feed it through B, because they have the same marginal PDF. I mean, that's the thing, right? By symmetry here. The vertical and horizontal coordinates have the same marginal distribution. So we can also use the same formula to generate samples from B. So that's our first idea. We're going to take 2 uniform samples. We're going to plug them in through their inverse CDFs to get samples of A and of B. And because we know that inverse transform sampling works, this should give us samples from A and B, which is what we want. In order to test this first idea, we're going to take a lot of uniform samples. Each of these guys is basically a point U1, U2, where U1 is uniform between 0 and 1, and U2 is uniform between 0 and 1, and the 2 uniform samples are independent. That's why we see that they cover the whole square. Okay, what is the joint PDF of a 2D random vector composed of 2 uniform random variables between 0 and 1? It's going to look like a square. All right, perfect. So now let's see what happens when we apply our idea. We plug in U1 through the inverse CDF of A, U2 through the inverse CDF of B, and this is what we get, which is somewhat disappointing, right? Because this is clearly not correct. We're not capturing the joint distribution of the triangle lake because the density within here should be constant. It's clearly not constant. There's much more density here. And the density here is 0. There should absolutely be no samples there. So what is going on? What's going on is that we're generating the 2 samples separately. So the marginal distributions are correct. If you took these guys and you just looked at the vertical coordinate and did, some kind of kernel density estimation or something like that, you would find that the marginal distribution is actually okay. It's this triangle that we derived. The marginal distribution is completely fine. Same for B. The problem is that the joint distribution is wrong. So what is going on? What is the problem? As I just said, our 2 uniform samples are independent. So when we plug them in through the inverse CDFs, those things remain independent. So we're generating samples from A and B that are independent according to their marginal PDFs. So the joint PDF of those samples is just the product of the marginals. But we know that the product of the marginals is not equal to the joint PDF unless the 2 variables are independent, which is clearly not the case for our example. What we really want is samples from the joint PDF, and the joint PDF by the chain rule is equal to the marginal times the conditional, not times the other marginal. So we need to sample from the conditional instead of sampling from the marginal. So we first, in this order, we can sample first from A and then sample from B, conditioned on that value of A. That's the critical insight to make this work. So in order to do that, first we need to derive the conditional distribution of B given A. So let's do that. Remember what is the conditional PDF of a random variable given another random variable. Essentially, we get a slice of the joint PDF where we fix the value of the random variable that we're conditioning on, and then we have to normalize so that this is a valid PDF, it integrates to 1. How do you normalize? You essentially divide by this guy integrated over B, which is just the value of the marginal at A. Super quick review of what a conditional PDF is. So now when we plug in it up here, we're going to plug in 2, and down here we're going to plug in 2 times 1 minus A. That's the marginal that we derived. We get this expression. And here you really need to remember which one is the variable over which you're computing the density, which is B, and which value is just a parameter that is giving you a family of conditional densities, which is A, because this looks like a function, but it's actually just a constant with respect to B. So essentially this tells us that here, once we fix A, these conditional PDFs of B are just constant between 0 and 1 minus A. In order to simulate from this conditional distribution, we need the conditional CDF. Now, we remember that we have a constant with respect to B, so the CDF is really simple. It's just linear, right? You integrate from 0 to B. What do you get? B divided by 1 minus A. So very simple. Now we need to invert this in order to apply inverse transform sampling. So we're going to set this thing equal to U. Okay, with respect to B, again, A here is fixed. We're conditioning on that value of A. I can't say that enough. A is fixed. Okay, so now we have that conditional CDF. We set it equal to U. So this is super easy, right? The inverse is equal to 1 minus A times U. Okay, that is the B such that if we plug it in, gives us U. Very, very different to what we had before because the conditional is constant, whereas the marginal is actually this triangle, so they're extremely different. All right, so our second idea is to take two uniform random samples, U1 and U2, and then first sample A by plugging in the uniform sample through the inverse CDF of the marginal. That's going to give us a sample from the marginal of A. And then we're going to condition on that value. And this is critical. You have to realize that this value here, we're going to plug it in there because we want the conditional distribution of B given that particular sample of A. Okay, we know that the conditional PDF is uniform, so we derive the CDF, the inverse, we plug in the second uniform sample through that inverse of the conditional CDF, and that's going to give us the appropriate, I don't know if appropriate is the best word there, but the sample of B that we actually want. So let's try our little experiment again. We have all of these uniform samples. Each point is U1, U2. And now this is what happens when we apply our strategy. So realize what we're doing. We're first fixing the vertical coordinate by sampling from the appropriate marginal distribution. But once we do that, then we sample something uniform in that interval. So that gives us the right distribution. Okay, this is how we manage to correctly jointly sample from the joint PDF of A and B. So what have we learned? We have learned that in order to simulate the joint distribution of multiple continuous random variables, a viable strategy is to essentially apply the chain rule and then be careful and generate samples conditionally on the previous samples so that you do capture the joint behavior of the random variables. And that's all I got. Thank you very much.